In this problem, we're looking at the U.S. population, which is currently around 313 million. This is expected to grow by 0.899% annually. Assume populations grow continuously. So continuous growth, we know, is given by the function, depending on how we write it, P, the population, is equal to an initial value, e to the rate times time. So in our case, we know to write an equation, the population, so we'll let P equal population, which will be in millions. And we want to model this as a function of years since 2012, so I'll let T equal years since 2012. And I know that initially there's 313 million, that's the 2012 estimate. The exponential growth base raised to the 0.00899, since that's our R, times time. Using derivatives, at what rate will the U.S. be growing in 2020 if the same percentage growth is assumed? So P prime we need to find first, which is going to be, well, in this case we have not just an x in the exponent, so we'll call this thing U. Here's our base is E, and 313 is A, and by the form of the derivative of an exponential function, it's going to be the natural log, the U prime times the natural log of B times A times e to the U. So U is 0.00899t, so the derivative of that is just 0.00899 times the natural log of our base, which is E, times the A value, which is 313, times e to the U, which is just e to the 0.00899t. Now the natural log of e is equal to 1, so that allows us to simplify this a little bit. And I'll just multiply 0.00899 times 313, which comes out to 2.81387. And that's e to the 0.00899t. Now I want to find P prime for 2020, which is 8 years after 2012. So I'll plug in an 8, and that gives me, I'm just going to go ahead and evaluate this in my calculator. That gives me 2.81387 times e raised to the 0.00899 times 8. And that comes out to about 3.02. Now, what are the units on this thing? Well, the units are in millions of, here we are, millions of people per year. And this is the expected instantaneous growth rate in 2020 if we continue increasing in population as fast as we have been.